Then let's talk about the model. In this particular case, the model describes the degree of importance for each variable in terms of flow sensitivity. Here, as you can see, this model M, okay, is a function from variables to real numbers between 0 and 1 that describes the degree of importance of each variable. Okay. We can train such a model with an off-the-shelf method such as Bayesian optimization. Okay. The high-level idea of learning is to represent variables as feature vectors and learn optimal weight for the features so that the model describe the actual importance of each variable. It's quite a common way to learn something, some model, right? So here is the same example. Okay. In this case, to prove these queries, okay, the question is which variable is more important in terms of flow sensitivity than others. So let's take a look at this example. Then we can obviously say variable W is not very important because the value of variable W is anyway unknown, okay, whatever analysis is applied. Okay, so this is not very important variable. Instead, this variable X is, okay, it seems very important in terms of flow sensitivity because it is assigned in different locations, so the order is quite important. Okay. In the same way, we can build a model that ranks the importance of variables as follows. Okay. So now we have this model that describes the importance of each variable. Then the central part of this work, okay, is to learn this controller. Okay, that takes a feature vector as an input, okay, that describes the current status such as memory usage and analysis progress and so on. Okay, and then this controller outputs the probability distribution on the range between, okay, 0 and 10. Okay, that means the percentage of variables that should be treated flow insensitively from now on, okay, from the particular moment. Okay, for example, if the output is 50, okay, if the output is 50, then from that particular moment 50% of variables will be analyzed in a flow insensitive way. Okay, this kind of problem can be formulated as a typical reinforcement learning problem, right? So here is the same example, okay, but now the interval analysis runs with the controller and model. Okay, let's take a look at this. It starts with the full flow sensitivity, as you can see. Okay, and suppose that it analyzed the first two lines. Okay, and now you can see we already have 6 intervals here, okay, which becomes very close to the resource budget. Okay, so in this case, the system triggers the controller, okay, and it will say that drop the least important variable from the flow sensitive analysis result, which means that coarsen the abstraction, okay, at this moment. So from now on, okay, the analysis handles variable W, okay, flow insensitively, right? So, but unfortunately, okay, sometimes such a decision is not that good, okay, like in this particular case, okay, here we could not reduce the memory footprint that much, okay, because W is already top, right? But if we proceed to the next iteration, then what happened? Then now we are about to run out of memory. We already have 9 intervals. Okay, So in this case, again the controller is involved in and say that drop the least two variables, okay, from flow sensitive analysis result. So we can save memory, and again we only have 6 intervals, as you can see, right? And then finally the analysis is finished without violating the resource constraint, okay? But as you can see, the analysis can prove the maximum number of queries, okay? Can prove these two queries, right? So let's see the practical impact. So in the paper, the performance of this adaptive analysis is compared to a previous approach that choose 10% of variables for flow sensitive analysis offline. Okay. The variable selection is also based on the same probabilistic model. Okay, but all the decisions are made before the analysis offline. Okay. Instead, the new technique makes decisions online. Okay, this is adaptive. So according to the experimental result, the conventional approach was not able to analyze larger programs properly. As you can see, it could not analyze some large programs because it runs out of memory, this amount of memory. And it could reduce false alarms by 27 and 30% compared to the flow insensitive analysis. But the online approach outperforms the offline technique in terms of both memory utilization and precision. So it could analyze all the programs, okay, all the programs without running out of memory, okay, with a given resource budget, okay. And also it was more precise than the conventional approach. It could reduce more false alarms compared to these conventional approaches. That is the adaptive program analysis.